two sets, two set of hypotheses. One is called the most specific no, set of most specific hypothesis, and the other one is the most general set of most general hypotheses. So S and G, and you can see those examples. So one of the interesting fact is that since you have so many consistent hypotheses, now if I give you a instance, say this is one instance. No, usually these are the test instances, or these are the instances which are not included in your training example, and that is why you are designing this classifier, or you are designing this, you are obtaining this hypothesis. So if I consider, for example, this instance, and you know that some of the hypotheses that will satisfy, that may satisfy this instance, and some of them may not. And depending upon them, depending upon the number, you can also have a different policy of assigning a level to this instance, whether it's a positive instance or negative instance, by applying some voting procedure. That means if you find majority is agreeing with certain levels, whether it is positive or negative, you give that level. So you take this particular example. So sunny, warm, normal, strong, cool, change. Yeah? This is the instance of a particular day, that description. So can you tell me that what are the hypotheses that would satisfy this instance?
All hypotheses will satisfy, sir.
Yeah, that's very true. Actually, the best way of looking at it is that you start from the you can alternately check with S and G, hypothesis in S and G, because you know that S is the most specific. So and all other hypotheses are general with respect to S. So any positive samples, any positive label in by any hypothesis in S must be positive in all other hypotheses. So you need not check that if it is already satisfied there. But suppose some hypothesis is not satisfied in S, and then what you should see that whether that hypothesis is satisfied of sorry, whether that instance is satisfied by any hypothesis in the set G. Now, if none of the hypotheses in the set G satisfied it, that means it's a negative example. That means none of the hypotheses in the Gaussian space also will satisfy, because that is the power of G. That is the interpretation. So if G rejects any hypothesis in G rejects any instance. So I'm just always confusing with the term hypothesis and instance. So one is hypothesis, the other is instance, which you are going to label. So if G rejects any instance, which means all the hypotheses in the Gaussian space will reject it. And if any hypothesis in S accepts an instance, all the hypotheses in a Gaussian space will accept it. Sorry. Let me go to another instance. Say, take this instance: rainy, cool, normal, weak, warm, same.
No hypothesis will be satisfied.
Yeah. So the check is that now you find this hypothesis is not satisfied. Sorry, this instance is not satisfied by an hypothesis in S, and also then you check whether what about the hypothesis in G, and you find none of them satisfies it. So which means that no hypothesis will satisfy. Let us have another example: sunny, warm, normal, weak, warm, same.
General will satisfy it, sir. But general will satisfy this.
Which are the hypotheses? Can you tell me?
So both of the hypotheses.
I didn't get the point.
In the G set.
The G set, which one? Let me use a pen, and I will be asking you this thing. Say, let me use this color green. Suppose consider these hypotheses. Is it going to satisfy it?
Yes, sir.
What about this one?
No, sir.
This one is not satisfying. It is sunny, warm, normal, weak, warm, same.
Yes.
Yes, sir.
I think this will also satisfy, no? This will also satisfy. This will also
Yes.
satisfy,
Yes, sir.
right?
Yes, sir.
Now,
Change the color.
oh, you are not able to see green. Okay, just a minute. I'm making it red then.
Yes, sir.
Okay. So this one and this one, they both satisfy, huh? They both satisfy this one. What about then? Then you should look for this two. What about this one? This one. What about this one? Is it satisfying?
No, sir.
No, sir.
So it is not
No,
satisfying.
sir.
Yeah. And what about this one?
Yes, sir. Satisfying.
This is
Satisfying, sir. Yes, sir.
What
Yes,
about
sir.
this will also satisfy? No,
No.
this is not, because the strong is not going to satisfy the weak. Huh?
Yes,
So,
Yes, sir.
so how many hypotheses it is satisfying? There are three, right?
sir.
Three hypotheses in the Gaussian space. They satisfy this instance. So it is 3 versus 3. It is difficult to take a decision. Huh? You can take any decision. Okay. So this is the kind of decision process that I was talking about. You take the last example in this case, say sunny, cold, normal, strong, warm, same. So can you tell me that?
First from G will satisfy,
First
one from G will satisfy,
Very good.
and the
Sunny
one,
and strong one will also satisfy.
Second, which one you are saying?
leftmost from the middle.
Second,
Most of
Yeah.
sunny and strong.
Yeah. So there are only two hypotheses which are satisfying. Is it not? Only two.
Yes, sir.
Other four are rejecting it, which means the majority says that reject this instance. Okay. So so these are the kind of policy that I was. Fine. So you can see that no, as I mentioned, that your hypothesis space is incomplete in the sense that some of the target functions, they are not part of your hypothesis because of your constraint that you imposed in the form of hypothesis. So uh, only if the target function exists in the hypothesis space, then all these algorithm will work. Otherwise, you will get an empty version space. So that is so for example, this I mentioned earlier also. Say sky equals sunny or sky equals cloudy, and this is a target function. And then this cannot be represented by your hypothesis space. The example what we have considered, that conjunctive normal form, in that way that cannot represent this particular target function. So naturally, with this kind of training examples, like you have two positive examples and one negative examples, and you can see that if I apply the candidate elimination algorithm, then your boundary, your set of most specific hypothesis, that's S, uh, till the second example, you can get a hypothesis. Moment you get the negative example, it becomes inconsistent. So they become empty. And actually, you get an empty version space. So this is the effect so if apply C algorithm as before, after first two T's, you get S is like this. But when you get but this hypothesis is overly general, because as you can understand that you assume that rainy also it should be also positive. But then when this third example comes, then you are looking at it, and then naturally you cannot get it. Your S cannot contain any hypothesis. Now, in the find S algorithm, this was the limitation. It was not looking at the negative examples. So what is required in that case? You require more expressive hypothesis space. But again, it comes with a price. So if you require more expressive hypothesis space, that means your hypothesis space will have, I mean, the size of the hypothesis space also increases. Not only that, it may happen that your hypothesis target function formation becomes too trivial. I mean, so generalization part is not very simple in that case. So we call them as unbiased learners when you do not put any kind of bias on the form of hypothesis. That means there is no limits on representation of hypothesis. So you can use full logical expressions and or not, any general expressions using and or not uh, that can be used to express an hypothesis. But the problem is that uh, in that case, you will find that no, given the training examples, you can exactly get an hypothesis, but no, that only fit only that set of training examples and no other. I mean, not only said that. I mean, it is not that. I mean, in that case, what happens that um, you are not really getting much information. So let me explain. Suppose you have these training examples where um, you have these are the set of instances, huh? x1, x2, x3, x4, x5. These are the positive, sorry, uh, it means x1, x2, x3 is positive, positive examples, and x4, x5 is negative examples. So my writing is a little confusing here. You have this with x4, x5 negative means x1, x2, x3 is positive. So if I apply the this candidate elimination algorithm with this kind of no, without any constraints on the Boolean expressions using and or not, then I can get a set of more specific set by no by considering the OR operations over x1, x2, x3. Like these are all positive examples. Similarly, for the for the general boundary, since we will be excluding only the negative examples, so I can put all examples of negative examples by this logic, and not in x4, x4 or x5. Now, these are the two boundaries. Now, there would be a number of hypotheses in between S and G in that Gaussian space, which are more general to S and less general to G, but which satisfies all these training examples, which are consistent. But actually, we'll find they are not really giving any information because you take any unseen instance, you will find 50% of them are satisfied by that set of hypotheses and 50% are not. So if you apply majority logic, it does not make much sense, right? So if you make the learner unbiased, doesn't mean that no, you are increasing the strength of your learner in that sense. It is not really helpful or useful to solve any problem. So inductive bias is required. Inductive bias, which means that you need to go to the domain. You understand what are the constraints in the domain. So that is the knowledge, right? That is the knowledge you are trying to put into your decision-making system, into your learning system. It is very important. So you need to put some constraints on the representation of hypothesis, and that would limit the, if, for example, this limiting connectives of conjunctions or allows learning. So that actually gives you a better generalization power while forming hypothesis. But I mean, I mentioned that's a bias. So let us understand then what is this inductive bias for a learning algorithm. So can I make a formal definition with respect to the directive system? You know that directive system is the system where by applying your axioms and arguments, you derive certain facts, you derive certain, you take some inference. Now, when we say that you are putting some inductive bias, it is basically inductive bias, again, some additions to those set of axioms. So in the deductive system, already there are established set of axioms, which we always know do not explicitly mention. So when we put place argument, some of the basic axioms are not really mentioned every time. But no, for when you are really going to put this inductive bias, you have to put those things. So if I consider inductive bias as the if I can present, you can represent this bias as a facts. and put them into your into the framework of your argument framework, then no, this all training examples, instance, and bias. So if I add with respect to training with the training examples and instances, like training examples and bias, I should say. Training examples means basically there will be instances and there will be levels. So if I add with them this bias, then if I apply the deductive systems logic, you should be able to get the same result. So that is the equivalent part. Say candidate elimination algorithm is one such example. So this is what inductive bias of learning algorithm. Any minimal set of assertions of B that is required such that for any target concept and training examples used to logically infer the value Cx of any instance X from B, D, and X. Okay, this is the bias. D is the set of training examples. X is actually any. So that is the idea that now if I apply any instance, and if you would like to get the result as the value of the target function on that instance, it should be the same by the deductive system if you include the bias into this system. That is the conditions. Consider some of the examples of inductive bias. You say rote learner. Rote learner is simply that you are memorizing the facts, and only whenever the facts are coming, whenever the information related to the facts, those are given to you, then only you can then you basically you declare that facts based on that instances. Only when so you are memorizing all instances with all levels. Whenever some instance comes, you just declare its level. So actually, it does not require any inductive bias. It is basically that's what is rote learner. So you record every possible instances with its facts or with its levels, and so naturally, this kind of learning, rote learning, is not very in a way, it's not very powerful in the sense that it is quite exhaustive. It requires a lot of memory, and also it requires a lot of time also, because you are going to search over the over your storage, over the knowledge base, and to get the instance, etc. But sometimes we use it. It is not that we reject it. There are some cases when they are powerful in the sense that exactly they will give you the result. Almost you do not have any error. So it's an error without any noise. So some of the examples of inductive bias, so far whatever we have discussed, for rote learners we have already mentioned that I do not require any inductive bias. Whereas if I consider the candidate elimination algorithm in the for forming this Gaussian space, we know that these are the things. This is the thing that has to be there as an inductive bias, that your target concept should be an element of that hypothesis space. Then you should get a Gaussian space which will contain the target concept. If the target concept is not there, then your Gaussian space would be empty. In the find-S algorithm, it is little more. I mean, not only target concept, but you also assume all instances that are not positive are negative. Now, as I mentioned, there is a limitation. Now, this fact you cannot check this consistency, whether it has maintained this consistency or not. You are not really going to check within the find-S algorithms, because it is not really looking at negative examples. So that is its limitation. So now let us consider what should be the computational complexity of this candidate elimination algorithm, which forms this Gaussian space. So one way of looking at it is that what is the size of the Gaussian space? Because it is not the size of the Gaussian space. It is basically, I would be more concerned on the size of these two sets S and G. That is what you are going to compute. Now, if the size is in the polynomial time, then also you have to say that check whether the computational steps are polynomial time or not. That is one thing. But now that we have already checked for every instance you are taking some action, but whether it is polynomial or not, that we have not considered. But one of the fact is that if the size itself, in the worst case, if the size itself is of exponential order, so you understand that you have to enumerate anyway those hypothesis set. So then it cannot be a polynomial time algorithm. It would be of exponential time. Unfortunately, that is the fact. We'll see that. So actually, this most specific set, that set of hypotheses, that is S, there you can say that it is linear. I mean, that can be shown. It is linear in number of features, the number of training examples, but the general boundary, there actually it is not so linear. It could be exponential. We have seen that so many combinations. I will give you one example. So in more expressive languages, also both S and G can do exponentially. But the order of processing examples significantly affect computational complexity. So that is another thing I mentioned earlier also. But whatever may be, since the size of G itself is exponential, so finally worst case algorithm, it should be. I mean, worst case means if you consider all possible different kinds of instances, there are certain instances where G could be bounded. G is not fallen. One instance I have already example we have seen. It is G is not growing exponentially. But there could be some instances where G can grow exponentially. So let us take this example. Say you consider this is n Boolean attributes, right? It is not H, that is n Boolean attributes. That means there are n literals. There are n attributes, so n variables are there. So dimensions. So dimension of your space is n. And suppose you have every Boolean attributes, that means it has only true and false values. So there are, I represent every Boolean condition by true and false values only. So a particular example, positive example, is given by this all true values. So a positive example is all true values. So let me use a thing. So this is a positive example. So all true values. So which means that I have positive example. And these are my negative examples. Okay. So these are my negative examples. So what should be the size of the version, size of the no set S and set G? If you apply candidate elimination algorithm, that would be more clear to you. So anyone can tell me? Since there is no taker of this question.
+1.
What is, somebody said something? Tell me.
Sir, n by 2 plus 1.
Which one? You separately answer. That size of
okay,
S?
okay.
Size
Size
of
of S will be 1 only because there's only one positive example.
Okay.
And G will be means not of all those training examples sort of. So it will be like n minus n by 2, which is n by 2.
How do you express the not of all those training examples?
I mean, I think.
So you have to consider
okay, yeah.
our representation.
Oh, okay. Yes.
Conjunctive normal form representation.
Okay.
Okay, so let me give this. Illustrate this.
Sir, the size of G should be 2 power n by 2.
Okay, how do you get it?
Because in first two attributes we can have one true, and for the next two attributes we can have one true out of those two. So that's why we can have.
Yeah, I think you are in the right track. You are telling. So let me elaborate a little bit what probably you are telling. Say you know that the first G would be all question mark. Okay, So and of course, no, you can say G1 also. It is in the first iteration when you get the positive example. Suppose this is a sequence by which you are getting these examples. So when you get this one first, so S1 is all T, and G1 would be say all question mark. So let me put it as G0. I mean, just in my case. So now when you get this particular my pointer is not shown. This is a problem. So when you are getting this negative example, then you have to modify. No? This is not going to be satisfied. I mean this is not consistent with this negative example. Is it clear? This is not consistent. So how do you modify this? You cannot put F here because no, as you can see, this is a positive example. If you put something F here, then that is not a general hypothesis with respect to this positive example. So your hypothesis has to be also a general hypothesis with respect to your hypothesis in the S boundary. So the two possibilities are there with respect to this. One is T all question mark, another is question mark T and all question mark. Is it clear? Given this negative example, there is only two such possibilities,
Yes, sir.
which are which forms this general boundary. Fine. So now let us consider you get this training example. So then what happens? This one also does not satisfy this training example because no next two question mark position will have this 2f. Moment it gets 2f, no, this is satisfied by this one, but this is a negative example. So you have to reject that part. Similarly, this one is also. So for each one of them, again, you will have, let me use arrow. Each one of them, you will have these things. You see that for this one, you need to have, once again, if I would like to include more general version, I mean general version, but excluding these negative examples, so this one needs to be changed into these two. So that's why it is one hypothesis can give you two hypotheses. Once you eliminate it, but in place of it, you have to replace it by these two hypotheses. Similarly, say this hypothesis will be replaced by these two. Is it clear?
Sir, can you repeat?
Yes, sir.
If somebody has asked some question. Okay. I hope it is. See, the thing is that since these are these two question mark needs to be replaced by one T question mark and question mark T to take care of these 2F, so that this 2F gets rejected. And you go on doing these things. That means that every step, for every hypothesis in the previous step in the general boundary will lead to two hypotheses. So you are multiplying by 2, and there are n by 2 steps. It would be 2 to the power n by 2. Okay. Fine. So you have this is the answer. Your size is 1 for specific most specific boundary, and most general boundary will have the 2 to the power n by 2. Now let me give you a bit more general perspective of this learning, and this is one kind of some of the basic I should say theory behind the computational learning. So this thing, this model, there is a learning model which is called probably approximately correct learning model. And with respect to this target function and hypothesis space, we can very easily understand this concept. And it says that suppose you have a consistent hypothesis. Now, this consistent hypothesis means that it will have training error 0, because so far our assumption is that we consider that's not assumption. Basically, consistent means it will be consistent with respect to all positive. That is the definition. For all positive examples and for all negative examples, hypothesis will be consistent. And naturally, since it covers all the training examples, so there is no error. There is no error in labeling. But actually, your target function may be something different. It's not, because no, you haven't looked into other instances which are not covered by your training examples, and there the values of your target function and your hypothesis may differ. And that is what is explained by this figure. I hope you have understood this diagram. As you can see that there are in the space, I have shown the partitioning of the space in a two-dimensional grid. So interior of the ellipses, those are the positive examples, and outside those ellipses are the negative examples. So these have been shown by this plus and minus sign. So in the C, which is a solid no, line for the ellipse, the positive examples are within that ellipse, and whereas the hypothesis H, you have the corresponding dotted line. So that also includes positive examples. So there is a common agreement. There is an agreement between of the positive examples by C and H. That is the common set. That is the intersection of these two ellipses. Whereas there are disagreements also. There are disagreements. So some of the positive examples, which are positive examples for for H, actually they are not really positive in the target function, which means your data has some error. Which means your data may have some error. Okay, so there your target function is not satisfying. And similarly, some of the negative examples in the target functions, they will become no, not only, sorry, I'm sorry, it is not data. Even the data, if the data is not data does not contain any error, these are all unseen examples. So in some examples, you will have which are positive, declared positive by H, they are not really positive by C. They are labels on it. So these are all false positives. Similarly, some of the examples which are labeled as negative by H, they are actually positive in. So these are all false negative. So these are the two types of errors that you get. One is false positive error, one is false negative error. And but you get error. You get error from this. So this error, let me call. So this is a true error. So training error is 0. Training error could be 0, right? So so your again, our assumption is that there is no error in the training data. Please modify my previous assertion. So, but now, so for that training error could be 0, but true error, that means with respect to the whole space, there could be mismatches between these two, and that is what is true error, which is not 0. So we let us have an consider suppose this error is expressed as a probability. That what is the probability that two levels differ, and that is what is the definition of the error. That is what is the definition of the true error. To denote that it is the error over the whole space, so we use this kind of curly D, this stylist D symbol, that is the population distribution symbol. Whereas the training examples, I will use simple D symbol. So with respect to this, let us try to understand what is meant by probably approximately correct learning model. As you can see that we have this particularly three or five things. One is C. C is the set of target functions. That is the class defining the target functions or concepts. So each target function is basically a concept. So it's a concept class, and which are defined over a set of instances X, and the form of the target functions is such that the instances, each instance has a length n. That is the length of the instance. Okay, like the set of 6-dimensional or n-dimensional attribute space. That is what is an instance. And L is a learner, some algorithm. So using a hypothesis space H, then this C is PAC learnable. C is that concept class is probably approximately correct learnable. It's a characterization of that class when this is the characterization that if for every target function in that C, and if you consider there exist two bounds. One is epsilon, which is within the interval of 0 to half, and one is delta 0 to half, such that the probability of such that the error of h is less than equal to e, that epsilon. That means this is the bound. That means true error is bounded by epsilon. So your hypothesis, it will learn an hypothesis whose true error is bounded by epsilon with a probability of at least 1 minus delta, right? So as your delta becomes smaller, with a high probability, it will learn an hypothesis whose error is bounded by epsilon. So if it is true, if there is any learner that for every target function, there is a high probability that you get a bounded, you get a hypothesis with a bounded error of epsilon, which should be small, at least which should be less than half. Otherwise, no, it does not make much sense. So then we say this is PSE learnable. This is a very formal definition. Oh, not only that, sorry. This should be done in the polynomial time in the order of 1 by epsilon, 1 by delta n, and size c. So that is the whole definition. So first thing, the objective is to get hypothesis whose true error is bounded by epsilon, and you should get with the probability of learning should be high. So that should be at least 1 minus delta, and your learning algorithm should be complexity of that algorithm should be polynomial in terms of this 1 by epsilon, 1 by delta, n is the input size, and also size of C. That means the size of the target function space or class of C. So this is something which is interesting. I mean, we try to characterize any particular algorithm with respect to this. So one of the basic question that is asked when you are trying to address this part, that what is the training examples? How many training samples are required to get a successful hypothesis with a high probability? Successful in the sense which is bounded by and true error of epsilon. That is a successful. So its successful hypothesis does not mean that it will be consistent over all throughout your input space. It will have some error, but the error would be small. Error would be bounded by some value epsilon, and with a high probability you should get it, right? So what is the how many training samples? What is as you understand that if you get more number of samples, your strength of your or rather the kind of strength of your hypothesis increases. That means you have seen more, so you are expecting that your true error should be less. Your true error should be less. So this is the thing. What is the number of samples? And question is put in this way, that how many samples required so that the version space consists of any consistent hypothesis bounded by an error epsilon. So you are considering that. So all in the version space you are having, it will in the version space means you will get consistent hypothesis with respect to your training samples. So which means the candidate elimination algorithm type of algorithm, which will give you all the hypotheses with which are consistent. But now what is the probability? But you would like to get those hypotheses bounded by error epsilon, right? And what is the how could you get a PSE learnable algorithm so that its probability could be high as 1 minus delta, where delta is small? That means a failure to detect any consistent hypothesis whose probability of error is greater than epsilon is delta. Maximum probability should be delta, and that depends upon also the number of training samples. So let us try to understand this. Now, one of the things, property that we'd like to see of the version space, we call it epsilon exhausted. That means if your version space contains all hypotheses, consistent hypotheses, naturally version space is set of consistent hypotheses, which has this property that whose true error is less than epsilon, then we say that version space is epsilon exhausted. So then you can pick any hypothesis, and no, that would be sufficient. So this is one very interesting theorem. It says that you can get some bound on the number of hypotheses on the or the so this is the thing that you can get some bound on the probability that the version space is epsilon exhausted, depending upon uh, the number of hypotheses in the hypothesis space. It has to be finite, and also the number of training examples, and depending upon, of course, the bound epsilon. So this is the theorem. It says that this probability of version space is epsilon exhausted. It is less than no, this size of the hypothesis space into e to the power minus epsilon n. For it is true for any particular finite hypothesis space for any learning algorithm. Now, the proof says that the proof comes like this: that suppose you consider there exists some hypothesis H whose error is greater than epsilon. That means whose true error is greater than epsilon. But actually, this hypothesis is in the version space, which means this hypothesis is consistent. Okay, so if I give you m samples, so those m samples are consistently labeled. So naturally, given a sample, the error of labeling, true error of labeling is epsilon. So if I say all m samples are labeled correctly, and that's why H is declared as consistent. So what is that probability? I have already given it. It should be 1 minus epsilon to the power m. I hope it is clear. Is there any doubt?
No, sir.
Fine. So if I consider that, so now if you assume that I consider only one hypothesis, for one hypothesis, this is the probability that this hypothesis being with error greater than epsilon, but still declared consistent. So if you assume in our version space there are k such hypotheses, right? If there are k such hypotheses, not in version space, in your hypothesis space. If you assume in your hypothesis space, you have k such hypothesis. See, the thing is that this H is included in the version space with probability 1 minus epsilon to the power n. Now, if k such hypotheses are there in the hypothesis space, so what is the probability that no any one of them will be included in the version space? It should be k into that, any one of them. It's all logic, right? It's an exclusive OR. I mean, you can simply add all these probabilities. So this is the probability that any of the k hypotheses that would be included in your version space. Is it clear?
Yes.
Okay. So now you can see that this particular fact k into 1 minus epsilon to the power m is bounded by this value mod h, that means size of h into e to the power minus epsilon m. That's little mathematical jugglery. So that's very useful, of course, this particular relation, and it is applied in many cases. So you see that e to the power minus epsilon is greater than 1 minus epsilon. If you expand e to the power minus epsilon, you will find e to the power minus epsilon has some more terms, right, which are higher, which are positive, which contributes to the positive term. So, and the first two terms are 1 minus epsilon, so it is greater than 1 minus epsilon. And that implies that k into 1 minus epsilon to the power m is less than k into e to the power minus epsilon m. And since k is a number of hypotheses from the hypothesis space, naturally k has to be less than size of the hypothesis space. So it's a very, I should say, the bound what has been shown, that is quite loose bound, quite loose upper bound, right? This is not a tight upper bound. K is much smaller, but no, I am saying that it is mod h e to the power minus epsilon m. I hope this proof should be clear to you. Is it clear? This is what is the proof. This says that no probability of version space is epsilon exhausted must be bounded by this. So what we say that no maximum probability of providing a consistent hypothesis with error greater than epsilon, that we would like to get delta, and that should be less than equal to delta. And when we put some more consideration, then m should be greater than equal to 1 by epsilon log mod h. I mean, you can make mathematical simplification, and this is the kind of m is the number of training samples. This is the kind of bound on m, and this is the lower bound. And overestimate, the size of version space is much smaller than mod h, so it's an overestimate. So this could be a smaller number also. And you can see m grows linearly with 1 by epsilon and logarithmically with 1 by delta. So that is the kind of m, and also grows logarithmically with size of the hypothesis. So one of the examples could be, suppose you have a set of target functions of n Boolean attributes in conjunctive forms, and each literal can have 3 values: true, false, and ignore, always 1. And we know that a hypothesis in the same conjunctive form of a literal, we have already discussed that it should be 3 to the power n. Actually, 3 to the power n plus 1. One null hypothesis is also there. And then, hence, m greater than equal 1 by epsilon n log 3 plus log of 1 by delta. So if I put some values, suppose n equal to 10, epsilon is 0.1, delta equal to 5%. So actually, you will find m is quite small, 140. Even it's a kind of overestimate, but still this number is small with respect to this conjunctive normal form. So there is another interesting concept that is involved. So one concept is regarding this PSC learnability and also the number of training samples minimum that you require to make it PSC learnable. The other concept is that what is the sample complexity of a hypothesis, which is where actually you may have the infinite hypothesis space. Now, there it means that you are trying to understand what is the capacity of your model. What is the capacity of your model? So one of the things that we consider, which is called dichotomy. So if I give you a set of instances in S, so then I can partition this instance into 2 sets, positive and negative. So that is called dichotomy. So when you partition is a given set into 2 sets, positive and negative examples, so you can get. So how many possible partitions are there in that case? Suppose I give you say 3 points, 3 instances. How many possible partitions? Anyone? See, each sample will have 0, 1 leveling. No?
8, sir.
8, right? 2 to the power 3. So it is 2 to the power mod s. So number of all possible dichotomies should be 2 to the power mod s. Now we call a hypothesis space shatters these dichotomies if there exists any hypothesis for a dichotomy so that to completely without any error it should resolve the dichotomy. So if there is a consistent, so that is consistent hypothesis for every dichotomy of this, right? So then we say that no, this H shatters, and there is a concept called Vapnik-Chernow-Nenki's dimension, which means that the size of the largest finite subset in X, that is the input space, shattered by a hypothesis space H. That is called this Vapnik-Chernow-Nenki's dimension. So it shows the power of your hypothesis space or the capacity of your hypothesis space. So if this size is large, your hypothesis is assumed to be more complex. So one of the bound, of course, in this in this number, this BC dimension, in a short form we call it BC dimension. So BC dimension of an hypothesis space, it should be less than equal log of that log 2 of hypothesis size h. Proof is very simple, because you know that if you have d instances, you require 2 to the power d distinct hypotheses. So at least which means that d could be, at most d could be the minimum, d could be the, if it shatters, d would be the, at least d would be the BC dimension. It could be more up to d plus 1 also. Then it requires 2 to the power d plus 1, which means that your d, which is basically representing the BC dimension, which should be less than log of h. Some of the examples that we can go through, that h is suppose hypothesis set of all intervals in real axis. What does it mean? That suppose all the points within this interval, they are declared as positive, and outside it all are negative. Suppose this is the hypothesis. Okay. Now, if I give you say certain set of points, and then you label them in different way, so what is the largest number that would be shattered by this h? Suppose I give you two point in the real axis, right? So you can shatter it, because if both the points are positive, you can declare an interval including those 2 points, just sufficient including them. If both the points are negative, you can declare which will be outside it. And if positive and negative, you can declare an interval, just one end should be in between this samples. But if I give you 3 points, can it be shattered? Suppose like this is the thing. So it shatters any pair of distinct points P and Q. Okay, suppose P minus 2, P minus 1. So these are the examples, any pair of points. But shattering means existence of any hypothesis sufficient. And say there are 3 points, which is like this: P less than Q less than R. Naturally, I mean, whenever you take 3 points, there are 3 distinct points, there will be some order, and there wouldn't be any shattering of this hypothesis. I mean, you cannot shatter P, R, and Q. That means, say, Q is, say, negative and these two are positive. It is not possible to get an interval which will classify, which will be consistent with respect to these training examples, which means, say, PR is positive and Q is negative. Is it clear? So what should be the BC dimension in this case? Because you have proved that for 3 you cannot shatter. So the BC dimension is 2. And there are other examples like set of straight lines in a plane. So in this case, as you see that you are trying to shatter points. That means you are making, if you consider a straight line, there are positive halves and negative halves. So the positive example should be in some, there are 2 halves basically. And depending upon the expressions, we declare one half is positive, another half is negative. So your hypothesis is that all positive samples should be in one half, all negative samples should be other half. So you can show that actually it can shatter any pair of 3 non-collinear 3 points. Now it is sufficient to have any 3 points. So collinear 3 points it cannot shatter, but if there exist any 3 points, that is sufficient. And then it need not be true for all instances of 3 points. That's what. But now if you take 4 distinct points, suppose this is the example. It has been shown at the rightmost topmost corner. There you can see that this is one example by giving 2 colors. Since you see that there are 2 lines. If you draw 2, so these 2 convex sets, they are intersecting. So there is from the geometry you can prove that there does not exist any line which will separate these two sets, right? So there exists one dichotomy given 4 points. There exists one dichotomy if the 4 points are fixed, for which there does not exist any straight line which will shatter it, which will which will be consistent with it, which means the VC dimension would be 3. So this is VC dimension, and in fact that's a general result in a d-dimensional space with d-1 dimensional hyperplane. VC dimension is d+1. So this example is that for 2-dimensional space you have dimension 3. For a d-dimensional space, the dimension will be d+1. Take the last examples, and with that I will stop today's lecture, and then we will have some questions. We can take some questions. So this example is about the rectangles. Now, if you consider all axis-aligned rectangles are the hypothesis space, that means like the example of ellipse I have given, for rectangles, inside the rectangle, suppose they are all positives, and outside the rectangle they are all negatives. There also you can show that the VC dimension would be 4 because it can shatter maximum 4 points. So there is a position in if there exist 4 set of points where you can get any where there exists a consistent hypothesis, consistent rectangle to classify them. I mean consistent with that leveling, but no, it is not with 5 points. So I think these are the few concepts that I mentioned, and you need to go through it. Still, I could not complete the whole concept learning part, but I will upload the slide set because the rest of the part is bit routine and a few slides are there. So you may go through them, and in fact, no, I am not going to discuss much about that because the other things are bit general. No, I will take that lecture. I will take that lecture of the quiz on Wednesday. I will take the rest of the part. But in your quiz, the syllabus should be till this VC dimension, okay, till what I have covered. And but still one part of your lecture is left out. And I will upload this slide in the module. You know that quiz we have set on this Tuesday evening from 8 to 9. I hope all of you already are aware of the time, and it would be held in the module. Okay. So let me stop here and let me take your questions.
Sir, please download the attendance sheet.
Okay, that's right. Okay, I have downloaded it, and please, if you have any questions, we have a few minutes to interact. Not many questions. I understand that now you need to read the book to get a few more concepts which I covered in these slides a bit. You have to really go through the proofs, and I hope you will be able to understand further all these things. Okay, then. So let me say goodbye today, and we will meet again. Tuesday there will be quiz, and again Wednesday we will meet in the lecture. There will be a weekly report that you need to submit. Thank you very much.